this video, we will introduce the first of the 5 major classes of organic reactions, acid-base reactions. The framework of a chemical reaction involves analyzing which bonds are broken and which bonds are formed. In many acid-base reactions, a proton H+ is transferred. This process involves breaking a bond with one molecule and forming a new bond with another molecule. This type of reaction is known as a Brønsted-Lowry acid-base reaction. In some cases, the two leftover partners form a salt. These resulting salts are formed by ionic interactions between two oppositely charged ions. There are 4 actors in every Brønsted-Lowry acid-base reaction: the acid HA, base B-, conjugate base A-, and conjugate acid HB. The acid is the proton donor, and the base is the proton acceptor. Once the acid gives up a proton, it becomes the conjugate base. Similarly, once the base accepts a proton, it becomes the conjugate acid. Here is a classic example of a Brønsted-Lowry acid-base reaction involving 2 compounds you're probably familiar with already. In this reaction, HCl, hydrochloric acid, reacts with NaOH, sodium hydroxide, to produce NaCl, salt, and H2O, water. In any acid-base reaction, it's important to identify the 4 key actors: the acid, base, and conjugate acid. In this reaction, HCl is the proton donor, the Brønsted-Lowry acid, and hydroxide OH- is the proton acceptor, the Brønsted-Lowry base. The resulting conjugate base is Cl-, and the conjugate acid is H2O. Additionally, we get a salt as the sodium ion Na+, and chloride ion Cl- form an ionic interaction to create NaCl. It's important to recognize that acid-base reactions are equilibrium reactions, where both the forward and reverse reactions occur to a certain extent. In the case of our example, the reverse reaction is also possible, but does not happen to any appreciable extent. To explain why, let's discuss what makes an acid-base reaction more or less favorable. In all acid-base reactions, the conjugate base is more negatively charged than the acid, and the conjugate acid is more positively charged than the base. The acidity of a molecule is directly related to its conjugate base's ability to stabilize a negative charge. Among these 4 conjugate bases, the ability to stabilize a negative charge increases with the electronegativity of the charged atom. Following this rule, we should expect HF to be the strongest acid among these 4, because its conjugate base, F- is best able to stabilize a negative charge. Conversely, we should expect CH4 to be the weakest acid among these 4, because its conjugate base, CH3-, is least able to stabilize a negative charge. Acid-base reactions that go from a less stable to a more stable anion are energetically favorable. In our example of HCl reacting with NaOH, the forward reaction is favorable because it goes from a less stable anion OH- to a more stable anion Cl-. Conversely, the reverse reaction is unfavorable because it goes from the more stable anion Cl- to a less stable anion OH-. As a result, this reverse reaction does not occur to any appreciable extent. In this reaction, OH- is less stable than Cl-, but this does not imply that OH- is generally an unstable anion. Let's briefly discuss Lewis acids and bases. Unlike Brønsted-Lowry acids and bases, which involve the transfer of protons, Lewis acids and bases are defined by their ability to accept or donate electron pairs. A Lewis acid is an electron pair acceptor, while a Lewis base is an electron pair donor. This definition expands the range of acid-base reactions to encompass those that don't involve protons. For instance, in the reaction between boron trifluoride, BF3, and ammonia, NH3, BF3 acts as a Lewis acid by accepting an electron pair from NH3, which acts as a Lewis base. Now let's discuss basicity. Basicity refers to the stability of a non-bonding electron pair on an atom. Therefore, the more stable a pair of non-bonding electrons is, the less basic it will be. Conversely, the less stable a pair of non-bonding electrons is, the more basic it will be. In summary, for any group of acids, HA, the strongest acid will have the most stable conjugate base. Additionally, the stronger the acid, the weaker its conjugate base, and the weaker the acid, the stronger its conjugate base. However, it's important to avoid the common misconception that weak acids are strong bases. This statement is incorrect, and the proper way to say this would be weak acids have strong conjugate bases. The last thing we will cover in this video are 2 key trends that affect acidity. There are a few other trends that we won't discuss in this video, as they require an understanding of content we haven't covered yet. Charge. In comparable situations, a species with lower charge density is more stable. As a result, we expect stability to increase as we go from O2- to OH- to H2O. The acidity-basicity trend tracks with these observations. Hydronium is the most acidic because it has the most stable conjugate base, and hydroxide is the least acidic because it has the least stable conjugate base. Water is a weak acid and has a relatively strong conjugate base, OH-. In terms of basicity, O2- is the strongest base because it has the least stable non-bonding electron pairs. OH- is slightly weaker because its non-bonding electron pairs are more stable compared to O2-, but it is still a fairly strong base. Finally, water is the weakest base because it has the most stable non-bonding electron pairs. Polarizability. As we go down the periodic table, greater polarizability stabilizes negative charge. Polarizability often correlates with larger, more loosely held electron clouds, and the more spread out a charge can be, the more stable it will be. For example, the iodide ion, being considerably larger than the fluoride ion, is more stable despite the magnitude of the negative charge being the same. As a result, Hi is a stronger acid than HF. As always, let's do some practice. In each of the following reactions, predict which species predominate at equilibrium. For the favorable reaction, identify the acid, base, conjugate base, and conjugate acid. Feel free to pause the video and try these problems on your own first. In the first reaction, protonated pyrrolidine reacts with methoxide to form pyrrolidine and methanol. The forward reaction satisfies the charges on both molecules, and as a result, we expect the species on the right to predominate at equilibrium. In this reaction, the protonated pyrrolidine is our acid, Ha+, methoxide is our base, pyrrolidine is our conjugate base, A, and methanol is our conjugate acid, Hb. In the second reaction, the methyl anion, CH3- reacts with hydroiodic acid, Hi, to form methane, CH4, and iodide, I-. The methyl anion, which is the conjugate base of methane, is not great at stabilizing a negative charge due to the small size and low electronegativity of carbon. Hence, methane CH4 is weakly acidic and will predominate at equilibrium. On the other hand, iodide I- is much better at stabilizing a negative charge due to its larger size and higher polarizability. As a result, hydroiodic acid Hi is a strong acid because its conjugate base I- can stabilize the negative charge very effectively. Therefore, in this reaction, we expect the species on the right to predominate at equilibrium. Hi is the acid, the methyl anion is the base, iodide is the conjugate base, and methane is the conjugate acid. Finally, in the last reaction, ammonia, NH3, reacts with water, H2O, to form azonide, NH2-, and hydronium, H3O+. Azonide, which is the conjugate base of ammonia, is not great at stabilizing a negative charge due to the small size and low electronegativity of nitrogen. Hence, ammonia, NH3, is weakly acidic and will predominate at equilibrium. Additionally, water, H2O, is not a very strong base because its non-bonding electron pairs are relatively stable. Therefore, in this reaction, we expect the species on the left, ammonia and water, to predominate at equilibrium. In the direction of the favorable reaction, H3O+ is the acid, NH2- is the base, H2O is the conjugate base, and NH3 is the conjugate acid. Let's move on to the next question. One equivalent of beta-mercaptoethanol is treated with one equivalent of NaNH2 and one equivalent of NH3 in the same reaction flask. Which group should we expect to be deprotonated first, the thiol SH group or the alcohol OH group? And by which base, NH2- or NH3? Feel free to pause the video and try this problem on your own first. The same principle of polarizability that explains why Hi is more acidic than HF also explains why thiol groups SH are more acidic than alcohols OH. Sulfur, being larger and more polarizable than oxygen, can better stabilize the negative charge on the conjugate base, the thiolate anion, after deprotonation. This increased stability of the conjugate base makes the thiol group more acidic. In contrast, the conjugate base of an alcohol, the alkoxide ion, is less stabilized due to the smaller and less polarizable oxygen atom. NH2- azonide is a much stronger base than NH3, ammonia. Hence, NH2- has a very high affinity for protons and will deprotonate the most acidic proton available, which is the thiol group. As always, thank you for watching, and I'll see you next time.